This meeting is being recorded.
Okay. So we are all set to understand MSSM actually. Okay. So we moved pretty fast actually. We came to MSSM very fast because we followed the superfield notation. So just superfields are essentially quantum fields on superspace. So where we introduce x mu, theta, theta bar with two Grassmann variables. And as I have mentioned it several times, I'm repeating it again and again, that there are only two important superfields which are important for n is equal to 1 supersymmetry. That means there is only one supersymmetric generator. Okay. So these two superfields are essentially the chiral superfield phi of dimension 1 and vector superfield. Vector superfield. So the chiral superfield is expanded phi is some scalar function, which is essentially the scalar superfield, scalar field, then a fermion, and an auxiliary field. The vector superfield contains a vector meson. Sorry, add one more extra. Theta bar, lambda bar, theta, 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 theta bar, D. Okay, so it has an auxiliary field called D, which is also dimension 2. And then we finally said that there are really two main functions which are important for us. The two main functions being W and K. W is nothing but your superpotential. And K is your Kähler potential. So there are certainties involved in these two. We'll come to it as and when we need actually. Okay. And there is a field strength superpotential, which is a curly W, which is given by D, D bar, D alpha, acting on B. Okay, these are your derivatives in superspace, essentially. Derivatives in superspace. So this gives you, W gives you mass terms and Yukawa couplings, K gives you kinetic terms and gauge interactions, and W gives you kinetic terms for gauge inverse and gauge bosons. Okay, so this total supersymmetric, in the limit where supersymmetry is exact, what we have is a Lagrangian, which is given by this W plus HC plus theta, theta, theta bar, K, theta, theta bar, okay, plus D2 theta, curly W alpha, plus, so that's it, okay. So this is the complete supersymmetric action, supersymmetric Lagrangian or supersymmetric action. In particular, it also contains, say, scalar potential, a scalar potential, which is, we call it a scalar which contains mod f square and mod d square. The scalar potential always has this form in supersymmetric theories. This you should remember, that the scalar's potential is nothing but f square plus d square. And that comes because when you expand these functions, you will have f square and d square, and you can club together those two f squares and d squares and write them as a scalar potential, because these are just terms made up of just scalar particles. This is SUSY invariant, by the way. This is all SUSY invariant. It's all SUSY invariant. And so, and we have solved for f. F is equal to dou phi I. Phi is equal to this. And d is equal to 1 by 2 GA phi I star tau A phi I. Okay. So this actually the d square terms is g square 1 by 2 dA dA. If you write it in this particular fashion, but essentially d. Okay. So this gives you the complete supersymmetric invariant Lagrangian, which also, so this f square plus d square also contains, is also supersymmetric invariant. It's also supersymmetric invariant. Okay. So the last time we did the supersymmetric QED, the action, SUSY QED action. And then we also introduced some, I just see the notation which I introduced for the SUSY QED. This was the recap. So we also saw the SUSY QED action, the final form of the SUSY QED action, which is SUSY invariant. As long as SUSY is invariant, we have these terms f mu plus I lambda bar sigma bar mu del mu lambda plus del mu EL tilde dagger del mu EL tilde del mu ER tilde whole dagger del mu ER. The reason why we need a separate left-handed field for the left chiral electron and right-handed scalar for a right chiral electron. This is because we need to match the degrees of freedom. The left degree of the electron has 2 degrees of freedom, so the the left-handed selectron has 2 degrees of freedom. So it should be a complex scalar. Okay. So that's how we write it, and we use the same notation also for MSX. Second, we'll start with del mu EL plus I EL bar sigma bar mu EL lambda EL dagger plus HC. So these are the Yukawa couplings, which we talked about last time. And the same thing also happens for the right-handed sector. So given that supersymmetry is inherently in chiral theory, inherently the way we wrote it down as a chiral theory, the left-hand, right-handed fields and the corresponding scalars are also different. Okay, the corresponding left-handed scalars and right-handed scalars are two different, completely different species. This is something, it's not easy to understand, but you should realize that these are two different species. These are two different fields. And this is your F term, and this is your D term. Okay, good. Now this is your, then we talked about the Feynman rules and so on. And finally, we talked about one more addition, what happens when supersymmetry is broken. So that's what I wanted to talk about today. So what happens when supersymmetry is broken is, we said there are three things which could happen when supersymmetry is broken. So which we call it as L soft, okay? So it's soft supersymmetry breaking. So this is LSQED, the supersymmetric QED. It's different from ordinary QED because you have a bonus. You have this kind of new Kava-like couplings. And the second bonus is that this coupling is no longer free coupling. Okay, the quartic coupling is no longer free coupling, but it is given by the gauge interactions. These are the two main differences you see. If you think of a supersymmetrized version of QED compared to adding, say, QED plus scalar QED. So a Lagrangian, if you just add QED and scalar QED and equate their masses, okay, and the couplings will not completely be supersymmetric invariant. Will not be completely supersymmetric invariant because supersymmetry also gives you gauge-no interactions, Fourtino interactions. Okay, and also it also determines that the quartic coupling should always be proportional to the gauge couplings, essentially. Okay. Now, any questions on this so far? Just before moving to MSSM, I just want to. Okay. Good. Now, now we talked about L soft. Okay. We talked about soft supersymmetry breaking in the last minutes. So we said just by inspection and by the argument of how supersymmetry should be broken and so on. So that if you want to break supersymmetry, one, mass of the electron and its electron should be different. So that means you give MEL tilde square is equal to ME square plus some delta. So you give an additional mass by some source. We'll see the source in a second, essentially. By some source, which is called, which is the SUSI breaking term. Essentially, it's a supersymmetric. So the total soft term or the total mass of the selectron, the supersymmetric partner of the electron, will contain a SUSI conserving mass, which is nothing but your F square term, and a SUSI breaking term. Okay, a SUSI breaking term. This is SUSI conserving, whereas this is SUSI breaking. A SUSI breaking term, which distinguishes it from the electron mass. So it should be typically heavier because we don't have something lighter than electron. So let's just say that it's typically should be heavier. So this is how we introduce, first of all, SUSI breaking by adding an additional mass for the electrons. And similarly, you add for the right-handed sector, ME square plus another delta. We'll come to qualify this delta in a second, actually, which is also SUSI breaking. So in principle, you can add for every scalar particle a mass term, okay, for every scalar particle or for a scalar partner of any matter particle, add a master. So one needs an add a master. Similarly, for every scalar particle means it's not okay. For every scalar partner, so let me just say partner of matter, just to be make sure that okay, matter particle, every scalar of a matter particle. The second one would be to introduce mass terms for gauge inverses. So normally you have what m lambda or a tilde, ma tilde is equal to the mass of the photon, which is ma, which is equal to 0. Okay. Now what we are saying is ma tilde, we can put a square because this is vector mass 0 plus some delta, which we can call it as ma tilde square itself as a free parameter, which is non-zero. So some delta, which is SUSY breaking, and the 0 is always SUSY conserving. Okay? The 0 could always be SUSY conserving. Okay, as long as it's 0 essentially. So you're adding terms where, so given a multiplet, a SUSY multiplet, like a vector multiplet or a chiral multiplet or a chiral superfield or a vector superfield, for the non-standard partner, you are giving a mass term. Okay. So, for example, in the chiral multiplet, it's the electron left-handed and the electron right-handed. There are two chiral multiplets. The scalar partners are the non-standard partners. They are given mass terms. Similarly, the 14O in the vector multiplet is a non-standard partner of photon, which is a standard model particle. So the non-standard partner of the photon is added a mass term. Okay, is added a mass term, which is called the 14O. If we add a mass to the 14O, then you can, yeah.
Hello. Yeah. So what order of the mass term we can add? I mean, is there any limit of, or is it depending on the theory that what order of mass term you can, like if it can be on TB scale or so?
Yeah. So the order of the mass term. Okay, the order of the mass term can be it depends on the experiment. Say, for example, so the present knowledge, if you want to put it this way. So theoretically, there is no limit. Theoretically, you can push it to any scale you want. Meaning, the point is that as long as it doesn't become, it depends upon, say, for models of supersymmetry breaking, which we'll come to maybe in a couple of lectures. We'll come to models of supersymmetry breaking. So, depending upon the models of supersymmetry breaking, okay, there are certain limits. But if you don't consider any particular models of supersymmetry breaking, you don't have a limit. You can actually break supersymmetry very heavily. But the point, what happened? I mean, so you cannot put it Planck mass, say, for example. So one of the particle is at electroweak scale, and you cannot put the other thing at a Planck mass, say, for example, or you cannot put it at a gut scale or something. Okay. Yeah, but you can try to build some models where this happens. But so because we want to keep it as close to the weak scale so that the quadratic divergences cancel and the large logarithms coming from the corrections also exist, essentially. I mean, also cancel, essentially. There are large logarithms which also cancel. And there are also some large logarithmic corrections which are to the loop corrections. These large thresholds should be controllable. That's the reason why we want them close to the weak scale, like for example around TeV, tens of TeV or something.
Yeah.
Okay. Otherwise, these logarithmic corrections can be large, but they can be extremely large. So your loop corrections coming from those can be, so you have to renormalize it in a different sense. But theoretically, there is no, the soft breaking doesn't have any limit. You can push it to any
Okay.
scale you want.
So typically when people work with a MSSM model or something, so one of the particle, let's say, is too heavy to be, let's say, decoupled limit, and it doesn't enter into your interactions of whatever particles you use to use in your analysis. So in that kind of scenario, is that we need to take care of fine tuning to be this
Right. I didn't introduce fine tuning. Okay. I didn't introduce fine tuning. So the limit can be set by fine tuning. So what is natural is your theoretical, meaning if you want, it's a theoretical constraint. If you introduce a new theoretical concept called fine tuning, you say that the corrections, the loop corrections, should not be significant that they change the, they should not be larger than the tree level masses of the particles. Okay, so that is essentially fine tuning. Say, for example, if the loop corrections are so large, okay, compared to the tree level corrections, that there are, say, 2 times, 3 times larger, that looks like there is some sort of a underlying fine tuning which is happening. Okay, that the total mass is loop plus the quantum correction, which should be small in general, is extremely large. So these loop corrections cannot be so large, essentially. So that's the basic idea, that compared to the tree level contribution to the, say, any particle, in particular to the Higgs mass, we'll see that. In particular to the Higgs mass, the loop corrections should not be very, very large. So that is, they should be comparable. Maximum, they should be comparable. But if you don't care this constraint, okay, that the loop corrections can be anything, I don't care. I'll organize my loop corrections in such a way that they are fine-tuned. I don't care about fine-tuning. I'll organize them that they fit the data, and rest of them, I push them all the way to the Planck scale. There is nothing stopping you. You can really push them very, very high, and it's a possibility. Then there is no relevance of supersymmetry, because supersymmetry is not protecting your Higgs mass. Okay. Supersymmetry is not protecting your Higgs mass. Okay. If you want to protect your Higgs mass, it should lie within very close to the weak scale, around 1 TeV or a few TeV, with a little bit of fine tuning. Okay. Yeah. Okay. So the third one we looked at was couplings. So you can have W is a holomorphic function. Holomorphic or analytic function, which is gauge invariant. But W always gives couplings to only to the fermions, right? Essentially, the couplings or fermion masses or so on. And so through the F terms, it gives you the scalar counterparts. But suppose if you write a holomorphic potential, so potential, say for example, like W, like for example, if you write a term dimension mu Bm, so we have in W in the QED, so minus M, so what's it, psi L, EL, ER. Suppose if I write the same thing in the scalars with the scalar fields instead of superfields, I write a soft term which is given by minus B M EL tilde ER tilde plus HC. So L soft contains, if I write such a term, this also breaks supersymmetry. This breaks supersymmetry because it's a dimension full term. This is B here. Okay, you don't have to parameterize this way. So you can dash directly as it. These are called bilinear terms. So this is dimension 2. It's like a mass term, but this breaks supersymmetry because it's not written in terms of superfields. Okay, if you transform this two scalars, okay, this breaks supersymmetry. You can just check it either in component formation or something. It doesn't come from W. It's not an F term. It takes the same form of W, but it doesn't come from W. It doesn't come from K. It doesn't come from any of the supersymmetric invariant potentials or functions. Okay, so this is SUSY breaking term. SUSY breaking term. But it has the form of W, except that you replace superfields with scalar fields. And it's holomorphic. That means it is not EL tilde star ER tilde, but it's EL tilde star, EL tilde ER tilde plus EL tilde star ER tilde star. Okay? Everybody agree with this? Okay. So for the QED, you can write a similar thing also for if you have Yukawa coupling. Say, for example, if in some other theory, there is a Yukawa coupling Yijk, phi I, phi j, phi k. So there is some Yukawa coupling in the superpotential in some other theory. So let's call it as some other, or let's call it as Yukawa theory. Okay. So if I can write an L soft, which is supersymmetry breaking, some Aijk, phi tilde I, phi tilde j, phi tilde k plus hc. These are called trilinear terms or A terms. These are bilinear terms or B terms. So all this together will form the total supersymmetric Lagrangian, which also breaks supersymmetry, So your total L SQED, broken SQED, is equal to L SQED plus L soft. So this is the form or the function we should remember. Okay. So this total number of terms which we will analyze will be a broken supersymmetric QED theory, which can work actually. So this will have the same forms. Okay, this will have a B term. This will have an gaugino masses. This will also have selectron masses, and so on. And now we have drawn all the Feynman diagrams. You can analyze it, put it in, I don't know, mat graph or something, and look for signatures and so on. So you can do all the game essentially. Okay. So, and so if you agree up to this, then we can start moving towards the MSSM actually. If you all agree to this.
So in this trilinear terms, all these superpartners should have charges that cancel to make this term gauge invariant, right?
Yes.
Only then we can write such a term.
Right.
Okay.
It is the trilinear terms. Remember, they're analytic. There are no stars here. Okay, they should be gauge invariant.
Okay.
There are some non-holomorphic soft terms also, which we will see later on. Actually, I don't know whether we will encounter them. In MSSM, we don't encounter them. Um, yeah, but there are certain terms like that.
Okay.
Yeah. So, but they should be gauge invariant. They should be gauge invariant. Okay. Okay. So let's. So now we know how to write supersymmetric Lagrangians. Okay. So we have seen the QED Lagrangian. Now let's try to do something called the minimal supersymmetric standard model. Okay. Here, one important thing is it's okay. So we want to write a supersymmetric standard model. That is very clear. But very important thing is minimal, because minimal is often a very highly abused word. Everybody calls their model as the minimal model, but here it has a very definite meaning. In this case, the MSSM it has a different meaning, and this is the most probed Lagrangian in the entire history of the universe. I think. Okay, more than standard model, I think MSSM has been proved. This is my feeling actually. Okay, so the number of people and the sheer amount of effort which has gone into understanding the MSSM is tremendous actually. So this is also called MSSM. So why it's called minimal? Minimal is the minimal content, minimal particle content required to build a supersymmetric standard model. So this is the minimal meaning. It's like using Occam's razor. That is the minimal particle content you would need to explain, say, for example, to construct a standard model, supersymmetric standard. Now, for doing that, we'll do it exactly like we do for the standard model. We revised the standard model, you remember. We always started with, in the first class, I thought, or second, we wrote all the particle content. And then we wrote the Lagrangian in different parts, okay? Like L gauge, L soft, so on. So we will do the very similar picture. L kinetic, L gauge, L Yukawa, and L super symmetry breaking. Okay. So just to recap. So recap of standard model. I don't have the slides or something here. But anyway, I think you will remember it. Okay. We'll do it once required. So we'll try to do it in the same fashion so that we have a one-to-one mapping between standard model and MSSM, so that it becomes easier. So first step, again, as in what we have done, what is the particle content?
Okay.
Yeah, anybody question? G standard model. It's SU3 times SU2. Yes, U and Y. Yeah. Anybody has a question? Okay. So the standard model is essentially the same gauge group. Okay, now we just have to supersymmetrize it. So what is the rule for supersymmetrization? What we always thought, meaning what we are seeing for QED, replace all the matter fields, quantum fields, matter fields, or fermionic fields with chiral superfields. Identify the fermions of the chiral superfields as standard model fermion fields. Okay, so this is the first step. So what are all the matter fields in the standard model? So you have, let's start with Q, which is essentially UL, DL. Let's put a generation index. So according to this rule, the Q should go into each component, each left-handed component or right-handed component should go into a chiral superfield. So the U goes to ULI, ULI tilde, which is a chiral superfield. D goes to DLI, DLI tilde. And this has a representation 3, 2, 1 by 6. Just as in standard model. Except the only difference between the standard model and the supersymmetric standard model is that both ULI and ULI tilde have the same representation. They transform as doublets. Okay, they transform as doublets, triplets under color group, doublets under SU2, and they have a hypercharge of 1 by 6. Okay, now what to do with right-handed fields? Right-handed fields, you have right-handed, okay, is equal to, I had to replace it with right-handed I, right-handed tilde. But then, if I write it in this notation, there is a slight problem because in the standard model, the left and right-handed fields have the same electric charge, hypercharge. Okay. Okay. So if you remember our superpotential, we said that if you want to write a gauge invariant term with the Yukawa coupling, the left and right should have opposite charges. So instead of making a superfield with directly with URI, I conjugate this UR superfield. I conjugate the UR superfield and make it conjugate the UR component fields, conjugate the UR component fields, and make a superfield out of it. Okay, so this will become essentially instead of this, okay, instead I use UR or UIC just to distinguish between this thing. UIC is equal to URC UIC tilde. Now UIC is equal to UR bar, okay, or this is nothing but UR star trigger, okay, okay, so that the field, okay, with the gamma 0 and everything essentially, okay, and URIC tilde is equal to UR tilde star. That's it. So that the charge becomes complicated. So I take these two fields, okay, I take these two fields and make a super field out of this, and I call it as UIC. Any questions on this? Huh? Okay. So the right-handed fields are always introduced in the conjugate notation. Then we have DIC in a similar fashion, which contains, okay, let's just finish the quantum numbers of UIC. UIC goes as 3 bar singlet minus 2 by 3. So it has minus 2 by 3. Okay, notice that it has minus 2 by 3. DI has DIC, DI tilde C. This has the quantum numbers 3 bar 1, 1 by 3. Okay, so now you have right-hand fields both in the down sector and in the up sector. So your quark sector has introduced at least 1, 2, 3, 4, 5 scalar particles corresponding to the 5 chiralities of the up and down quarks essentially. Times 3, which is 15 essentially. So for 3 generations. What is at the leptonic sector? In the leptonic sector, so these are called, all these things are called squarks. So all these things are called squarks. So all the tildes are all called quark. We'll come to leptonic sector in a second. So you have stops, S bottoms, both left-handed and right-handed. Then you have a strange charms, subs, down, etc. In the leptonic sector, we have Li, we have left-handed electron or left-handed neutrino, and the corresponding charge lepton. So this is also there, and so this is your ordinary neutrinos, which contain they are contained in the hypercharge minus for half, essentially. So this means these are called neutrinos. These are called selectrons. So, or sleptons. EI is equal to EIC, EI tilde C. This has 1, 1, 1. That's it. Hypercharge 1. This is a right-handed selectron or sleptons, essentially. So this essentially completes your matter spectrum. Okay. There is only one particle which is left in the matter spectrum, matter, or in another sense, which is called the Higgs sector. Okay. Before going to the Higgs, sector, let's introduce the gauge sector, essentially the vector superfields. So every gauge boson is mapped to just give me a second. Okay, so every gauge boson is mapped to a vector superfield. Field with the vector particle in the maze vector particle identified as the standard model gauge boson. Okay, straightforward. We can do that. So you have, so how many gauge bosons you have? So gauge bosons for the strong sector. Okay. So let's call it as VS A. So there is G mu A, and then there is G tilde A, which transforms 810, their octet under sp3 group. So these are your ordinary gluons. These are your gluinos. These are how many gluinos essentially? How many gluons are there? There are 8 of them. There are 8 gluinos. Okay, there are 8 gluinos also. Okay. We normally don't distinguish them. We saw gluino mass is so and so and everything. We almost treat it as a single particle, but actually there are a bunch of 8 of them actually. Okay. Okay. So Then SO2 has W mu I, and then W mu, not W mu, W tilde I. These are essentially called V nose. Okay, and these are your W bosons. They transform as 1 singlet 3 0. And finally, for the hypercharge, we have B mu, B tilde. So this is your B meson. So your B nu. It's 1 1 0. Okay. So this is, you have introduced your V nose, B nose, and so on. So okay. I forgot to tell something about supersymmetry, which I promised I'll tell, but okay, I'll tell in a second actually. When I come to that part of the Lagrangian. Okay. Now we have to worry about, so this gives you sort of the particle spectrum of matter, particle spectrum of the gauge, but we also need the particle spectrum of the Higgs. We need 2 Higgs bosons. What do we need? The minimal. So the minimal here corresponds to 2 Higgs bosons actually in the MSSM. Okay, we need at least 2 Higgs bosons for 2 reasons actually. For 2 reasons. One, to write down Yukawa couplings.
This large man.
Both up type and down type fermions. So for example, because the reason is, remember the W, the superpotential is the superpotential. Hello, you can hear me?
Yes.
Yeah. The superpotential is holomorphic. So if you cannot use phi tilde to generate, normally what we do is we use phi tilde to generate masses for the uptype quarks. It's not possible to do so. Okay, because phi tilde requires phi star, so we cannot reuse it. So we need to introduce an opposite hypercharge. So the only solution is a new superfield with opposite hypercharge. Okay, so second thing, the way we introduce the chiral superfields, we want to introduce a chiral superfields associated with the Higgs. Okay. For each Higgs field. Okay, let's just say there is only one Higgs field, say for the Higgs field, say, let's just say, and then we'll the reason actually. Field identifying the scalar as the standard model particle. Now, compared to the matter sector, this is different because in the matter sector, we are introducing the fermion of the chiral superfield as the standard model particle. Okay, but now here introducing a new fermion, thus introducing a new charged fermion as charged means charged and resistant gauge group as SUSY partner. So if you introduce any new fermion, you will end up having chiral anomalies because this is a chiral superfield essentially. Okay, and these are because it's a chiral theory anyway. Okay, the standard model is a chiral theory. So you're going to introduce chiral anomalies. So if you want to introduce cancel the chiral anomalies, you need to introduce one more fermion so as to cancel the anomaly introduced by this particular fermion. Okay, so that is the reason why we need to introduce two chiral superfields, such that because we are identifying the scalar as a standard model particle, because we are introducing new fermions here. Okay, we are introducing new fermions as SUSY partners. So to cancel anomalies, one more fermion with opposite hypercharge is required. So that's the reason why we need two Higgs doublet models, two Higgses. So the minimal supersymmetric standard model by definition is a two Higgs doublet model. Okay, is by definition a two Higgs doublet model. But we'll see that it is slightly different compared to the regular two Higgs doublet model. So let's look at the two Higgses which we introduce. H1 will be H10 and then H10 tilde, H1 minus, H1 minus tilde. So this one's one Higgs doublet, which say transform as 1, 2, minus 1 by 2. Okay, so there are these are your scalars, and the tildes are your fermions. These are called your Higgsians. Okay, these are your Higgsians. So the Higgsians are fermions. Okay, Higgsians are fermions. That we should remember. Okay, that's it. Okay, and so this is the second field, H2 plus, H2 tilde plus, H2 0. This has the opposite hypercharge. So you have your second set of Higgsians. So the minimal supersymmetric standard model, okay, contains 2 Higgses. Otherwise, it just follows the regular rule that every matter particle is mapped into a superfield. Okay, chiral superfield. So Qs are mapped into a chiral superfield. U's are mapped into, okay, except that there is subtle problem with the notation because you're introducing conjugate fields, but otherwise, you're just, as far as degrees of freedom are concerned, you're introducing, what do you call, you're just following the map. The only difference comes with the Higgs sector. So the earlier map, what we did for QED is the same thing. So you look at the chiral representations of the fermion, every fermion you replace it with chiral superfield. Every vector you replace it with the vector superfield. But when it comes to the Higgs boson, okay, the Higgs should be replaced by one chiral superfield, but that doesn't work because it doesn't give you completely couplings and so on. So, and also it doesn't cancel the anomalies because, okay. So introduce 2 Higgs doublets, okay, 2 Higgs doublets, one for the up type and one for the down type, so that you can have conserved supersymmetry easily. Okay.
Sir,
So,
is this need to be same masses of those 2 Higgs?
pardon?
So these 2 Higgs need to have same masses or can be different?
The Higgsinos, we didn't come to the masses as of now. As of now, just we are talking about the particle content. It turns out the final analysis is complicated actually, because if you just take the Higgsino spectrum, both of them end up having the same mass. Okay, but that is not the full solution. What happens is the Higgsinos, the neutral Higgsinos mix separate, because the main complication compared to QED to the standard model is that there is electroweak symmetry breaking. The Higgses get a web.
Yeah.
Okay, so when the Higgses get a web, you can do it in a smaller theory also instead of the standard model. When the Higgses get a web, the Higgsinos start mixing with other fermions of all the same charges. So all the neutral fermions mix with each other. All the charged fermions mix with each other. So gauginos and Higgsinos mix. So during that mixture, this Higgsinos become something called charginos. Higgino-gaugino mixture, which is charged, is called charginos. Higgino-gaugino mixture, which is neutral, is called neutralinos. So if you take the pure Higgino limit, yes, both the Higgsinos are the same mass.
So that depend on the coupling basically.
Yeah, but that doesn't stay as it is, because there is no pure Higgino in real sense. Unless the electroweak, unless it's very heavy, then there is a pure Higgino. Almost 90% Higgino you can have. Okay, that's a possibility. I agree. Yeah. Yeah. Any other questions regarding the particle spectrum? Okay, so let's continue. So let's now, given this thing, we'll do the same thing like what we did for QED. So we'll start with writing the Lagrangians, the superpotentials, and so on. So, okay, we'll start writing this thing. Actually. Okay, yeah. So let's start doing that. So what are the 3 functions we had? Right, the gauge kinetic function is set to 1, but the starting function is the Kähler potential of the standard model. So the Kähler potential of the standard model essentially is given by the kinetic part, gives you the kinetic part exactly like what we did. So d2 bars square sum over SU3 SU2 U1 phi beta dagger e power g v, okay, phi beta. Okay, so what it means, okay, let me expand this expression. That means that if they are colored quarks, okay, the three colors and the three representations, say for example in the SO3 color representations, okay, so colored quarks, colored, meaning in the colored space, okay, how do I write it? 1 second. Okay, so Q1, Q2, with the three colors of quark, there is a 3, and then e power I g as g mu of the gluon superfield A sitting here, Vg, and then whole dagger, and the same thing Q1, Q2, Q3. So this is the first term you can write down. So this, if you can expand it in terms of the Q color, okay, dagger 1 plus I GS, like what we did for QD. So the Q diagram Q gives you the, for all the colored quarks, analytic terms, and then it gives you the interactions with gluons. So not just the kinetic terms for the quarks. Sorry. Yeah, so then we have for the weak interactions, you have again the same Q, but this Q will be not the colored part. This will be Q dagger. Okay, L weak. Okay, so this will give me L strong. L weak, Q dagger E power G W superpotential corresponding to W field A Q. Similarly for the left-handed leptons, E power G V W L plus so on, so on. All the left-handed fields. And finally, for the hypercharge. So this, if you expand, gives you the interactions for the with the quarks with the W bosons, and also gluons and gluons. Sorry, and also for the gluons essentially. Okay, and here this also will be d power 4 theta. L hypercharge would be integral Q dagger E power G or Y B Q plus U dagger E power G Y B corresponding to U. This is Q. Okay, U plus d dagger e power g prime, sorry, this should be g prime y d b d plus L dagger e power g prime y L. And also this one contains all the right-handed fields also, because the hypercharge is true for left-handed as well as for the right-handed fields. So the entire thing, d2 theta, d square theta. Okay, so this gives you interactions with the W and B gauge bosons and P nodes and B nodes. Okay, plus kinetic terms for all the quarks and leptons, plus kinetic terms for all quarks and leptons. Okay, so this is about the K potential. Any questions here? Okay, very good. Okay. So then we come to superpotential. So the most general superpotential invariant under SE2, SE3, sorry, I should say SE3, SE3 times SE2 times U1 is given by okay. So the superpotential, I wrote it explicitly in terms of two parts. Okay, let's go through them slowly and understand these terms essentially. And the first terms, the first three terms, and the first three terms, these three terms are essentially your Yuka couplings. This gives you for the up type quarks, this gives you for the down type quarks, and this gives you for the charged electrons. Now, this term is the term which Amandeep was asking. So this term is gauge invariant. It's dimension full. These things are dimensionless. All these Yukawa couplings are dimensionless. So remember that the superpotential maximum dimension it can have is dimension 3, and these three terms saturated. But it also allows for dimension 2, lesser dimension terms, essentially, which is this one. Now, this term is allowed because H1 and H2 have opposite hypercharges. So H1 and H2 will become an invariant term because they have opposite hypercharges, and this term is allowed. And this term goes under the name of Higgsino mass term. So this term goes under the name of Higgsino mass term. So, okay. This is, okay. Now, there is something else happens here, which is a consequence because of supersymmetry, which is a consequence of supersymmetry. And it's a consequence that the L1 and H1 have the same quantum numbers. L1 and H1 have the same quantum numbers. And this is the consequence of that. See, L1 and H1 have the same quantum numbers, but in supersymmetry, there is nothing which distinguishes, which tells you that this is a Higgs and this is a lepton. The gauge symmetry is not going to tell you, okay, this is a Higgs and this is a lepton. In the standard model, the Higgs lepton distinction comes because there is also the same problem happens that L1 and H1 H have the same quantum numbers. The distinction happens because they are different Lorentz representations. Say Higgs is a scalar, L is a fermion, and automatically this takes care of the lepton number conservation. Okay, so here at the level of the gauge symmetry, you don't have a distinction between lepton and Higgs at the level of gauge symmetry. Okay, because, and at the level of Lorentz symmetry also, you don't have distinction. You don't have distinction because H1 is a chiral superfield, L is a chiral superfield. So supersymmetry doesn't distinguish between a L1's a leptonic superfield and a Higgs superfield. So wherever there is a Higgs superfield L1, I can put wherever there is a Higgs superfield H1, I can put L1. And that's precisely what I'm going to do. So mu H1 H2, I can put Li H2. So I introduce three new terms here. Now what happens is, as a consequence, this term breaks lepton number. That's the reason I separated them out. So there is no automatic lepton number conservation in supersymmetry. So L1 I can put here, okay, wherever there is a H1. So H1 I put L1, and He I can put again LLE. This is Li H1. Again I replace it to as Li Lj EKC. Okay. So each Yukawa coupling, so the leptonic Yukawa coupling becomes another lepton number violating coupling. The down type quark Yukawa coupling becomes another lepton number violating coupling. So these three become one of the most problematic lepton number violating couplings essentially. So these are called lepton number violating couplings. Okay, these are called R parity violating couplings also. We'll come to that in a second actually. In addition to this lepton number violations, there is also a combination of three singlets, which is gauge invariant. So if you take U, D, and K, DD, DDU, DD, U has a hypercharge minus 2 by 3, D has minus 1 by 3, D has minus 1 by 3, or U has minus 2 by 3, D has 1 by 3, 1 by 3. So this total together is still gauge invariant if you take into consideration SU3 indices. So you can form an SU3 singlet out of 3 triplets. Okay, out of 3 triplets, you can form an SU3 singlet. So if you take the color charge combination, the color charge will get contracted in correctly, and so this term will be a gauge invariant quantity, okay, which is called Berio number violating number. This is a quark lepton Berio number violating term essentially. Okay, so purely because the leptons, the supersymmetry cannot distinguish between scalars and leptons, scalars and fermions. Okay, you end up having this problem that where there should be scalars in a Yukawa coupling, you can put leptons because they have the same quantum numbers, and this will end up giving you lepton number violating couplings, and another combination gives you a baryon number violating couplings, essentially baryon number. Okay, so together they are disastrous in a superpotential. Together they are disastrous because a combination of baryon and lepton violating coupling can lead to some fast proton decay essentially. What does fast proton decay mean? Here, fast is really fast, actually. Okay, reason is so typically, you know that protons are extremely stable. They are stable at the order of 10 power. Does anybody know the number? 10 power 33 years, essentially. Okay, so they're pretty stable. Protons are pretty stable. If you break this limit, it's called fast proton decay. Okay, if you break this limit, then this is called fast proton decay. So this limit comes from super K. Which searches for proton decay. Now, the presence of baryon and lepton number violating couplings, as I told you, leads to fast proton decay. How does it lead to? But before doing that, let us see what are these couplings actually. So what these couplings are. So for example, any term here, let's just expand one term here. So let's expand, say for the example, the top Yukawa coupling. So let's see what this top Yukawa coupling looks like. It gives you Yukawa couplings. So this gives me HU, IJ, QI, UJC, H2, theta, theta. Okay, so this is a theta, theta component. So this I expand it as HU, IJ, UI, UJC. These are superfields. Remember, these are superfields. I have not expanded them into component fields here. Minus DI, UJC, H2 plus. Again, theta, theta. Now let me expand them into component fields. So this gives me HU ij. The component fields, how many I'll get essentially is, I get, say I take the psi out of this, another psi here, and a phi here. Okay, and then I can repeat this combination. So I can keep psi u, psi u j c, okay, psi ui, psi u j c, phi of h20. Now then I take a scalar for the first term itself. I take a scalar, so I take phi u tilde I, okay, then psi u j c, psi h20. I take a fermion, because remember the superpotential always give you only Yukawa couplings. So you have to form Yukawa couplings from these three superfields, taking one scalar in each of them at a time. So if I take a scalar in H, in the next term, I can take a scalar in UJC. In the next term, I can take a scalar in UIC. So each of this thing gives you essentially three Yukawa couplings, all of them with the same strength. All of them with the same strength. Okay, and you got this point, that this will give me three Yukawa couplings, all of them with the same strength of this one, and this will give me another three Yukawa couplings, again all of them with the same strength. So this entire term, one single term in the superpotential, gives you six Yukawa couplings of the same strength. Okay, six Yukawa couplings of the same strength. So let's write them down. So now I take psi ui, phi ujc. Okay, phi is a scalar essentially, psi h20. And this will become the second terms, these three will be psi di, psi ujc, phi h2 plus minus phi d tilde I, psi ujc, psi h2 plus minus psi di, phi ujc, psi h2. So these are your six Yukawa couplings coming from one single term in the superpotential. One single term in the superpotential. So let's write them in the compact fashion. HUIJ, UI, UJC, H20 plus UI tilde, UJC, H20. And this is your in the component form. UJC tilde, H2 tilde 0. So this is a Higgsino quark coupling. Okay. Di UJC H2 plus minus Di tilde UJC H2 plus minus Di UJC tilde H2 tilde plus. So these are all the possible couplings. Now, so this gives me Higgs quark couplings, and then it also gives me Higgsino quark couplings. Both these things are possible. Okay, so in the same fashion, if I have R parity violation, if I have R parity terms, okay, let's just take say a term like lambda double time. IJK, UIC, DJC, DKC. This gives me quark, quark couplings. Okay. And this gives me lepton, quark couplings, or it also gives me lepton, quark couplings. Okay, we'll see it in greater detail in the next class, but I just wanted to introduce this kind of couplings. So here you have a coupling which is couples a lepton and a quark, a particle which couples at a vertex both a lepton and a quark. This is like what? It's a leptoquark. It's a leptoquark, essentially a coupling of a lepton with a quark, essentially. Okay, so this is a leptoquark like coupling. Sometimes there's a reason why R parity violating couplings are also like leptoquark couplings and so on. So essentially. Okay, so these are all the couplings which end up having. So if you have, say, for example, a proton is made up of 3 quarks. So one of them can go up to a quark, which goes into a lepton and a quark. Okay. Okay. And this will be something else, essentially. So this will be some Q tilde, say, for example, and this will be some lepton. Okay. And this will be some other Q. Okay. So this will be, okay. This will be like Q. So you can have a lambda double prime coupling and a lambda prime coupling. So if you have such an interaction, and if MQ tilde is around 100 GeV, so tau P or gamma P, okay, would be around MQ tilde square. You can integrate this thing and then have this effective operator, which will be just like QL effective operator, which is very, very large. So this gives me tau p's of the order of seconds, 24 meaning of the orders of seconds, essentially. So if you want, them to be, okay, here I had to put lambda prime, lambda double prime. So this has to be 10 power 33 years. This product, lambda prime, lambda double prime, should be equivalent to 10 power minus 24. They should be so suppressed. These leptoquark-like couplings, if both of them are present, okay, to avoid fast proton decay. They should be so suppressed, essentially. Okay, so in the next class, I'll introduce R parity and the variance of it and so on. So, okay, so the essential point here is that if you just write a W1 and W2, which are gauge invariant interactions in the MSSM, the W2 contains terms which are highly, dangerous. They lead to fast proton decay. But proton decay is the only example I had talked about because it is the strongest constraint one can have from experiments. But it leads to a host of phenomena which are like R parity violating phenomena. Essentially, there are a host of phenomena which you can have. So you want to somehow say that W2 has to be suppressed. So we need to think of some symmetries, symmetries which suppress W2, because the presence of W2 will lead to fast proton decay, and it's disastrous. A symmetry to suppress W2 is called R parity. It's a discrete symmetry, okay? And imposing W2 on the superpotential will set it to 0. Okay, so for all practical purposes, by imposing R parity, we'll come to the exact form of R parity and everything. Okay, essentially it's a Baryon number, Baryon number. Okay, R parity. I can just use the formula essentially. So if I just have some sort of a form U1 symmetry, so the discrete symmetry or U1 symmetry, such that R parity is given by -1 whole power 3b minus L plus 2s on the component fields. I'll do it explicitly again. On component fields, this is the form of the R parity essentially. Okay, if you, we'll talk about also in superfield notation what it means. Okay, if you impose it on component fields, this is the form it has: R parity minus V 3b minus L. Okay, imposing this R parity violation completely suppresses W2, and that way you can keep proton safer. Okay, proton safer. So, okay, let me stop here. It's already 11:10 or something. Okay. So, any questions so far today?
So can we have
Okay.
R parity? I have a question. Can we
Pardon?
have R parity and still like this proton decay is forbidden, like in some scenarios? Can we have such scenarios? Can we introduce some symmetry so that R parity is there, but proton decay is forbidden?
No, R parity, yeah, R parity conserves the photon. Now, what happens is if you R parity will always conserve the photon. There's no problem actually. Proton will be conserved. Okay, when R parity is imposed, you can violate R parity and still conserve the proton.
Yeah. So what scenario is there? Like, what do you need?
So for example, one popular scenario which has been explored is, for example, for proton to decay, you need both lambda double prime as well as one of these two. Okay, so let me draw separate lines for this one. This is one color and this is another color. Okay, I don't know, both colors seem same essentially. Okay, this color. Okay, so both these colors are required, both the couplings. So lambda double prime is required as well as lambda prime or lambda or epsilon. One of these things is required for proton to decay. Now you can think of variations of R parity conservation in which lepton number is violated, but baryon number is conserved. Okay, baryon number is conserved. So that means only this term goes to 0. Only this term goes to 0, other things are there. So those are very, very popular actually. They have been very popular. And this gives you neutrino masses. They can escape limits from colliders, meaning compressed spectra, and so on, so essentially. Okay. And proton is safe. Proton is safe. Okay. And then you can also have the reverse. You can conserve lepton number but the baryon number is also violated.
Mm.
Okay, so people thought this violation useful for baryogenesis and so on. So it didn't work out because of the spellerons or something, but yeah, people, both these cases have been considered essentially. They're very popular. And you can have symmetries which are much more complicated than R parity, which are more, this is Z2 symmetry, but you can have Z3 symmetric R parity and so on. So in that case, what happens is only certain terms of these couplings are allowed. You can make that, and those things in which, it's a whole game to play. You can allow only certain couplings are allowed, and then you can keep proton conserved and still violate what do you call meaning not conserve proton but still violate one of the baryon number or electron number.
Mm.
Okay, but
Okay.
you know, one should remember one thing which is not emphasized too much, but R parity is only valid at tree level in a sense. Okay, it's a okay, let me put it this way. If we at dimension 4 level, R parity is a very good symmetry. If you consider an effective field theory with higher dimensional terms, R parity conservation is very, very hard. And the constraints are very, very strong. So when you're considering effective field theories of MSSM, you will easily violate baryon and lepton number with higher dimensional terms. Okay, and R parity is violated. R parity is only good at the dimension 4 level of the superpotential. So beyond dimension 4, you have to be very, very careful actually, because you can violate it very strongly again with higher dimensions. And then you have to impose further symmetries, which would, though violate R parity at higher dimensions, but still conserve proton. Okay. Yeah, you were saying something. Prabhat, you were saying something?
No. Thank you.
Yeah.
Thank you.
Yeah. Okay. Any further questions?
So in
Okay.
MSSM, one thing, in MSSM to have neutrino masses or to get the origin of neutrino masses, we need R parity violation.
Yeah, it's true. If you don't, you can. There are ways. Meaning, because this, you can have lepton number violation. Like I said, you can have a variation of R parity violation, in which you can conserve baryon number but violate lepton number, and that will give you neutrino masses. But the neutrino masses are slightly heavy. It turns out to be some combination of some type 3 seesaw mechanism. Okay.
Okay.
And then with R parity violation, okay, say lambda double prime, lambda prime, sorry, you can get neutrino masses very nicely. It's very, they give you contribution at tree level as well as at one loop level. And then what happens is their masses which you get, typical masses are around MEV region. Okay, so you need to suppress the R parity violating couplings further by 6 orders of magnitude to generate neutrino masses of the order of EV. Say for hundreds of GeV or 1 TeV lepton masses, so you get neutrino masses of the order of MEV. So mu is of the order of MEV. So if you want to generate smaller neutrino masses, lambdas have to be changed to 10 power 5 to 10 power minus 6. So so there is some seesaw mechanism. That seesaw mechanism only brings the scale from 1 TeV to MEV region. If you want to further suppress, you have to fine tune these couplings further. Okay. But yes, for neutrino masses, they are very nice. And people thought of using it for leptogenesis and so on. So they're pretty good actually. They're useful. And the soft terms corresponding to this R parity violation is also pretty good. You can generate something called soft leptogenesis and so on. So. And yeah, that's it's a good thing. The baryogenesis using lambda double prime didn't work out because of the speleron thing. Like it's like a gut baryogenesis. Why it didn't work out is exactly the same reason which we discussed when the gut baryogenesis happened. So when you have so gut baryogenesis happens with using a negative delta B, whereas spelerons gives you positive delta, and so they wash out whatever is previously existing baryon asymmetry. So baryogenesis didn't work out for R parity violation. But right now, again, they're sort of interesting because they have a good candidate for a leptoquark. And for the B anomalies and so on, so they're a pretty good candidate. And also to escape the limits from large hadron collider. So R parity violation is again back in sort of business actually.
Okay. Thank you.
Yeah. Okay. So Tuesday I'm not teaching. So let me just see the calendar. Tuesday is a holiday, I think. Yeah. Tuesdays I'm not teaching, but we'll meet again on 6th. Do you want it online or do you want it offline? You just let me know, and then we'll do it.
So online, I mean, it will be better for me because
Yes, most of
Okay.
us are in home.
Okay, so 6th also we'll do it online. Okay.
Okay. Thank you, sir. Thank you.
Thank you.
Okay.